Okay, good morning, everyone. Welcome to our first session with the RAPv5 team of the Global Systems Lab. And they're going to be the new RAP version 5 and HRRRV version 4 systems that are going to be implemented. NCEP currently scheduled for May 26th. Right now, I've got everyone, all the participants muted. James Kenyon is going to be giving a presentation, and then what we'll try and do is unmute everyone, and you can ask questions, and we can have a discussion. In the meantime, you could also feature or type your question into the GoToWebinar interface. So with that, let me turn it over to James.
Hey, great, Jeff. And yeah, before I go into full screen mode, I can see some of the other panelists here, some of my colleagues. So I should acknowledge Curtis Alexander's on the line. He's the overall project lead for RAPv5 development. Ed Zoke as well. He helped to contribute some of my case study material. Eric James is on the data assimilation team. He's also done important work for HRRRAS Smoke, which we'll talk about. I see John Brown, who's the head of our model physics team, and Tara Ladwig on the data assimilation team, who's done important work for the HRRRD data assimilation system, or HRRRAS, which we'll talk about. So these are some of the panelists I see joining us. Also, Ming Hu just dialed in, also on the data assimilation team. So I'm now in full screen mode. Jeff, are you able to see that okay?
Yes.
Okay, sounds good. We'll just get rolling this morning here. Again, I'm representing the whole RAPv5 development team out here at Global Systems Laboratory in Boulder, Colorado, representing a lot of work with contributions also from NCEP EMC, in particular the model evaluation group out there, and NCAR here in Boulder. Let's see. Here's how I advance. I just got to figure out how to advance my own slides. There we go. The RAP and the HRRRV are known to you all. These are NOAA's hourly updating weather forecast models. You see their domain in that center panel there. We have the 13-kilometer rapid refresh. This will become RAP version 5 later this month. And then we have two HRRRV domains, one over Alaska and one over the CONUS, HRRRV version 4. These are at convection allowing scales, run at 3-kilometer horizontal grid spacing. The RAP and the HRRRV really represent 10 plus years of research and development. These are of the same pedigree as the former RUC model, the rapid update cycle. That became the RAP model around 2009, 2010. And then the HRRRV model was introduced, first implemented early 2014. And now we're looking at the final implementation of the RAP and HRRRV later this month. And then subsequently, we'll pivot from a work-based implementation into an FV3 DICOR for subsequent implementation. So this is just the next iteration in an evolution of these hourly updating, radar assimilating regional models that NOAA and the National Weather Service are running. So some current RAPv5 shortcomings that we know about, and we'll try to address that in the briefing today. A lot of this, some of the key themes that we've heard from the field over the years. First among them is that the HRRRV is not quite yet true day-ahead guidance. So after this upgrade, we'll actually have a 48-hour HRRRV forecast every 6 hours. That's an extension from the current 36 hours. And we'll have a 51-hour RAP forecast also every 6 hours, but there'll be a little 3-hour lag there. There's also some problems with the 2 to 6 hour convective evolution, particularly with organized convection. So after the upgrade, we're fairly convinced we have more accurate convection forecasts, in part attributable to the HRRAS, the 3-kilometer ensemble data assimilation scheme that we'll begin to be using. We've known of a daytime warm bias and also a tendency to be aggressive with erosion of low clouds and stable layers. So after the upgrade, we'll have a better representation of subgrid scale cloudiness. That's going to be an important contribution to those problems. And there's also been no existing guidance on smoke transport. We've run a HRRRAS Smoke experimentally now for a few years. but after the upgrade, the smoke transport will be in line with the main HRRR model. So you'll have a full smoke transport and the meteorological coupling as well. And again, this upgrade is scheduled to occur later this month on the 26th. So there's quite a few HRRR changes. I won't go into all of them. I'm just going to go into the topics here in the red. But broadly speaking, we can think of these changes as involving either the surface characterization, data assimilation, the model dynamics and physics, and also the post-processing. Some of these that we want to talk about are the FBCOM data going into the HRRR initialization. This is going to improve our representation of the Great Lakes. Also the VIIRS and MODIS fire radiative power. This is an important part of the HRRR smoke treatment. I'll spend a few slides talking about the HRRR data assimilation system. This is really a key component to how we're improving the HRRR initialization and making better use of available observations. We'll talk about the model dynamics and physics, smoke transport, use of a small lake model for our small interior inland lakes. We'll talk about removal of the microphysics latent heating limit and the use of the NSSL implicit explicit vertical advection. So this is an important contribution to improved severe storm representation, and also some significant changes to our post-processing. That includes how we're rendering cloud cover, some changes to our variable density snowfall algorithm as well. And then we'll wrap up with a case study here in the end. So RAP and the HRRR, again, they're well known for hourly updated radar assimilating regional forecast models. The sheer quantity of observations that are assimilated every hour are remarkable, spanning radar wind profilers, WSR-88D, aircraft, surface, and satellite. Some of those observations are listed here in their quantity there on the right-hand side. This is not going to change with that next implementation. We're still going to really focus on using this rapidly updated information to improve short-term forecasts. What is going to change quite a bit is the actual underlying engineering of the initialization itself. A good way to illustrate this is with this sort of this flow chart, how HRRRv4, that's the current operational model, is initialized from the RAP. So you have this top tier here in blue. This is the 13-kilometer RAP. And then in this bottom tier, the 3-kilometer HRRR is in green. Some key parts here is that at every 15 minutes, we're simulating radar reflectivity 3-dimensionally in this 1-hour pre-forecast. And that's starting from just downscaling the RAP to a 3-kilometer grid. So here's the HRRR initialization occurring here. We do this pre-forecast. We bring in the GFS ensemble. We do our final data assimilation, which includes hydrometeor observations. And then we launch a forecast. Again, this is how it's currently done in operations. With this new HRRR version 4, we're initializing from the HRRDAS. So we're somewhat severing the previous relationship that we had with the RAP. Instead, what the RAP is going to do is initialize the HRRDAS, and then the HRRDAS is going to initialize the HRRR. We're still making use of these radar reflectivity observations and another iteration of GSI hybrid where we're bringing in the background error covariance. But now it's going to be provided by the HRRDAS, and we're still going to be doing the hydrometeor analysis as well before we launch that final forecast. So we should spend a few slides then just describing what we mean by the HRRDAS, and this refers to the data assimilation system. Really, this is a data assimilation ensemble. Has the same grid characteristics and the physics as the HRRR, but we have some initial sources of spread. We initialize this by bringing in the RAP mean and 36 GDAS members. These are the global ensemble perturbations. Bring this down to a 3-kilometer grid. We introduce HRRR soil moisture perturbations. Then we launch 36 1-hour forecasts. That's a pretty heavy lift computationally. We have to advance 36 model states every hour by 1 hour. So effectively, this is doubling the computational expense of the HRRR. But we want to develop an appropriate amount of ensemble spread, but also keep this ensemble really anchored in the observed atmospheric states. So we stop that forecast at 1 hour. Again, we bring in the radar and conventional observations. We bring in the cloud observations. We arrive at 36 new initial conditions, and then we just repeat this process. So we're still really aggressively assimilating observations. We have a tight localization that really controls the spatial scale of influence of any given observations. This is really key for what's appropriate for a 3-kilometer ensemble. And we're analyzing these variables listed here below. So what's the final upshot of doing this? This is expensive to do, as I mentioned. So out of these 36 HRRRRs states, we're deriving the ensemble mean and the background error covariances. And these are really key components for arriving at our initial conditions for this deterministic HRRRv4. And I'm showing this sort of schematically down here in the bottom. So the key idea here from running this data assimilation ensemble is that we're improving a deterministic forecast through better use of the available observations. It's a storm scale ensemble DA at true 3-kilometer horizontal grid spacing. A related project from this is the HRRR forecast ensemble, or HRRRE. That's shown in this right-hand panel here. This is still experimental, but it's still going to be really the prototype for future implementation. And we're still very much evaluating it in such things as the ongoing spring experiment. It's a key part of the Warn on Forecast project. So this is really just done by subsetting 9 of the 36 members and actually launching then a forecast ensemble. So again, that's experimental, but HRRDAS is going into operations, and that's a key part to how we initialize HRRRv4. We'll illustrate that perhaps with a case study. This is from June of last year, how the HRRDAS contribute to better convective evolution. In this case, we'll go into the central Great Plains. I'll first call your attention to this center panel here. This is the observed MRMS radar reflectivity 12Z on the 21st of June. You see sort of this double QLCS structure across eastern Nebraska, Missouri, and Iowa. So really some complex convective evolution, and subsequently that produced sort of this swath of some damaging wind gusts, and you see in that subsequent SPC storm report map right below it. On the right-hand side, it's a collection of forecasts from the operational HRRRv3 on that day. So the preceding 0Z forecast out to 12 hours, the 3Z forecast out to 9 hours, 6Z out to 6 hours, 9Z forecast with a 3-hour lead, and then finally the 12Z analysis. And you see that the HRRRv3 sort of struggled with that double structure. It had the broad details correct in terms of a QLCS advancing southeast, but some of the details just weren't quite there. On the left-hand side, though, we have the accompanying HRRRv4 initialized from the HRRDAS, and it was much better, even out to 12 hours, at sort of heralding that double QLCS structure. And so really we attribute that better forecast and that consistently better forecast with these 3 subsequent initializations to the use of the HRRDAS. So that's a nice convective case study there. Let's next pivot to the HRRAS Smoke capability. And previously we had HRRAS Smoke that was being run experimentally as sort of a standalone model. We call it the HRRAS Smoke. But with this upcoming upgrade, that's going to now be merged into the mainline HRRRv4. This is going to be a single tracer. That's what makes this computationally affordable. And a lot of this work was done by Eric James and Ravan Ahmedov here at Esrel GSL. Really impactful work at a time when wildfires are starting to impact particularly the Western US, but we're going to bring it up here in the Eastern region briefing as well. Key ideas here is that VIIRS and MODIS are these space-based instruments that can provide fire detection. Based on that fire detection, we map fire radiated power onto the HRRR grid. From that fire radiated power, we parameterize the smoke emission and the plume rise. And here's an example on the right-hand side, just a west to east cross section centered on Southern California. You get a sense of the scale of these smoke plumes. This spans 450 kilometers in the horizontal and 0 to 9 kilometers in the vertical. So these wildfire smoke plumes are really penetrating deep into the troposphere. Once we have that, we're then off to the races. We have full coupling then between meteorology and the smoke. So there's feedback on the predicted clouds, on the precipitation and the radiation. Here's a case from 2017. So perhaps it's going to be the West that sees most of the real air quality impacts, but some of these largest smoke events clearly reach all the way to the eastern part of the CONUS. It might not be such a surface health impact, but we see a lot of the radiation impacts as well, suppression of daytime 2-meter temperatures, and perhaps you get a lot of media inquiries as well as you start to see those smoky skies late in the summer. So again, it's worth mentioning here in this forum. Next, we'll move on to how we're improving lake representation, both in the Great Lakes and in these smaller inland lakes. Here's an image from July of last year, skin temperature from HRRRv4 and the operational HRRRv3 there on the right-hand side. First, I'll call your attention to the Great Lakes, and no need to circle those, they jump right out. You notice how different those lake surface temperatures are. HRRRv3 is unrealistically cold for mid-July, whereas HRRRv4, much more realistic lake surface temperatures. We're attributing that to use of the FVCOM lake temperatures from an ongoing collaboration between ESRL and GLERL. So we're bringing in FVCOM that's more appropriate for initializing the Great Lakes, as opposed to using sort of this NCEP SST data set that we've been using previously. And for these small lakes that I'm calling your attention to, including Lake Winnebago in Wisconsin, we're using a lake model within the WRF. And so that sort of allows the lake state to evolve with the model itself. And you see that these inland lake temperatures are very different. You can just see that from a stare and compare. And that, again, arose out of some feedback we were getting from field offices about unrealistically cold inland lakes. Let's just take a closer zoom in here. This is, again, the same day, but you can see some of the detail here. In this case, we have westerly flow off Wisconsin, so we have this upwind driven cooling. Again, it's being provided externally via our linkage with the FVCOM data. So we don't have to treat this in the HRRR, but we're initializing from that data. And again, you see the small inland lakes here across southern Wisconsin, much better represented for mid-July. Let's talk about Great Lakes winds. Those have been improved. Some of this is due to improved surface layer physics that we have in the MYNNN surface layer scheme. But here's a buoy comparison that was provided to us from GLERL. In this case, it's Lake Superior, but this is probably fairly representative of all of the Great Lakes. We're looking at 6 different buoys on Lake Superior. And really, you're looking at a histogram of wind speed versus frequency. OBS are in black. The existing operational HRRR is in blue. And then the upgraded HRRRv4 is in red. And with this upgraded model, you see there's a reduced overprediction of these low wind speeds, say around 5 knots or so, and a reduced underprediction of the higher wind speeds, say in the 10 to 15 knot range. So that's pretty good news, I would imagine, perhaps for the marine grids. Also, just for lake effect snow prediction, we're getting the better momentum over the lakes. And just from the bulk aerodynamic arguments, that's going to help to us with more appropriate fluxes during lake effect snow. So we're happy to see better winds over the Great Lakes. We'll go into that a little bit more in a case study in the end here. But here's just an example of some improved lake effect snow guidance, HRRRv3 on the left versus HRRRv4. This was provided to us during the model evaluation group evaluations this previous fall and winter. In this case, we're looking at December 2019. MRMS composite down here in the bottom right, you see this really dominant band just south of Buffalo. Much better represented in HRRRv4 as it is in HRRRv3, where there's some placement and intensity issues. Also, the more fine scale bands across northern lower Michigan look much more plausible in HRRRv4 than they do in HRRRv3. So again, we are mainly attributing this to not only the FVCOM ice fraction and lake surface temperatures, but the better model physics as well, and including those over lake winds, which are really modulating those lake surface fluxes of sensible latent heat. Let's now go into, again, a warm season application. Talk about the full microphysics heating and the use of an explicit vertical advection scheme from our collaboration with NSSL. Here you're looking at some forecasts from May 2018, HRRRv3 on the left-hand side, the operational HRRRv4 on the right. First, we're looking at max updraft vertical velocity, really from the surface to 100 millibars over the previous hour. So the scale here goes from 0 to 40 meters per second. Previously, we've really sort of throttled the microphysics heating temperature tendency that's used in the HRRR. That was a way to really guarantee numerical stability. Without throttling that, we would run the risk of model crashes. Now, with the use of this NSSL IEVA scheme, we can get rid of that limitation altogether in the microphysics temperature tendency, and also get rid of the vertical velocity damping that we previously had to apply in convective situations. So you see these gray pixels where now we're seeing routinely velocities that are exceeding 40 meters per second in some of these most intense thunderstorms. So this is what we're seeing as a result: the stronger updrafts in thunderstorms, and also more coherent updraft helicity swaths. These U8 swaths are really the signature of mesocyclones in the HRRR model. So these become sharper, more intense, and more coherent, perhaps longer lived too, with these supercells that we see in HRRR version 4 as a result of using this IEVA scheme and relaxing that previous constraint on the microphysics. Subgrid scale clouds have also been a big focus in our model physics development. Really the key idea here is that we can't just rely on a microphysics scheme to provide the cloud information in the RAP and the HRRR. Even the HRRR at 3-kilometer horizontal grid spacing is nowhere near resolving shallow cumulus clouds, shallow stratus clouds, thin ice clouds aloft. So the key idea here with subgrid scale cloud is that there can be thermodynamic variability within this sort of 1 delta X grid volume, both temperature and water vapor, and you can have these cloud fractions within a model grid volume, fractional cloudiness. But that variability is subgrid, it's unresolved, and so we have to parameterize that. In the RAP, that includes deep convection. In the HRRR, of course, deep convection is explicit. But in both the RAP and the HRRR, we are looking for better ways to represent this unresolved shallow cumulus, thin stratus, and ice clouds aloft as well that are thin. So some of the key changes for RAP version 5 and HRRR version 4 are really relaxing the previous constraints on the mixing ratio of subgrid scale clouds, improving the representation of the cloud fraction, and also going after the optical properties of these clouds, the effective radii of these cloud hydrometeors. So that really improves how these cloud information are being presented to the radiation scheme. I can give you a qualitative sense of this. This is another stare and compare visual with the GLOW's visible image on the top. This case is for 5 June 2019, and also a HRRR version 4. You're looking at upwelling shortwave flux back out to space. So this sort of mimics a visible satellite image, HRRR version 4 on the left, and HRRR version 3 there on the right-hand side. And we're just calling out with these ovals some areas to call your attention to. One, this area of Farewell cumulus over Maine. Really not much of a hint of that in the operational HRRR. Looks much more plausible in HRRR version 4 here on the bottom left. Also with this fair weather shallow Q across New York and Pennsylvania in that gold oval. And looking out west with that marine strato Q, looks somewhat paltry in HRRR version 3, much more plausible in HRRR version 4 on the left-hand side when you compare it with GOES visible. So this is again largely attributable to the improved subgrid scale cloud representation, largely led by Joe Olson, the lead MYNN developer out here. We see improved retention of stable layers in stratus as well. Here's a case, in this particular case, it's Denver, but it's not unlike the cold air damming scenarios that you see across the Appalachian Piedmont there out east. In this case, we're looking at 35-hour cloud ceiling forecast. So in color here, we have the cloud ceiling in thousands of feet AGL. Denver there called out just for reference. And you see this quick 3-hour loop of the GOES multispectra. So you see the low clouds really hanging tough. This western cutoff here is where the low clouds are up against the foothills of the Rockies. It's mixed out down to the south, but Denver stays socked in on this particular day. This is really shallow inversion layer stratus near Denver behind the cold front. Ceilings mixed out in Denver and HRRR version 3. but it's still maintained in HRRR version 4, even here at 35 hours. That's something that we would really struggle with in previous versions. And if we just overlay the associated soundings coming from the HRRR, you see not only has Denver mixed out in HRRR version 3, so it's gone subsaturated. We've really lost a lot of that stability that we had before in the inversion. That inversion is much sharper in HRRR version 4, and we've maintained that layer of saturation. So that's good news for these low cloud forecasts. Besides the physics, though, we've also focused on how we're rendering the cloud cover in the processing. So these are the grids that actually get out from the GRIB2 files and eventually make it into the AWIPS workstations. Here's an example of how we would represent low cloud cover for this forecast in October 2019. This old method had a lot of inherent smoothing, and importantly, it only looked at the explicit clouds coming from the microphysics. So you see these really smooth edges that weren't quite physical. With this new method, though, we're deferring entirely to the cloud fraction that's coming out of the model physics. And so that allows a much more faithful rendering of these cloud edges, both for the fog and stratus that you see across eastern Colorado, and also this for this shallow queue across South Texas. So there's no inherent smoothing, and we think that's a better way to go for these 2D renderings of what's really a 3-dimensional field in the model. Also want to talk about a revision to the variable density snow to liquid algorithm that's used in the HRRR for snowfall accumulation. This again has been a nice advance from previous versions, which just had a simple 10-to-1. The current operational variable method is shown here in solid. So you have the lowest model layer temperature ranging from -20 to +5 Celsius. Previously, this was quite capped, at about 13-to-1 or so. With this new variable method, it can cap all the way up to 17-to-1 for very cold temperatures. So we can produce a much more snow depth when it's appropriate to do so for cold temperatures. No change for grapple. We could improve this in future versions as well. We're looking at ways to improve our use of an entire vertical profile instead of just the lowest model level, and also using more physics variables as well. So thanks to Ed for this slide here. We'll look at a case study now, a good way to wrap up with the lake effect snow, 18 to 19 December 2019. Thanks to Ed. This was kind of this modest event, again, 18-19 December 2019, both for Michigan, kind of the northern Great Lakes and the eastern Great Lakes as well. This third shade of orange is 12 to 18 inches, so kind of two maxima here, one south of Buffalo and another northwest of Syracuse. At this time, the snow squall terminology was beginning to enter the public lexicon. So you see the Weather Service in Buffalo sort of aggressively messaging how these two images were taken 10 minutes apart at the Rochester Airport, and the New York State Thruway Authority emphasizing that these two images are 10 miles apart on I-90 running east to west. So let's get into the HRRR forecast. HRRR version 3 is here on the top. First, let's just look at the old static 10-to-1 snow accumulation. So this is really just taking the raw accumulation of precip out of the model, just giving it a factor of 10. HRRR version 3 again on the top, HRRR version 4. These are both 36-hour forecasts. On the left, initialized 6Z on the 19th, on the right, 12Z on the 19th. HRRR version 4 being quite a bit more bullish with these lake effect snow bands, in particular across these areas that we mentioned previously. But that doesn't really, isn't fully evident until we go here to the variable density, and that's really when HRRR version 4 shines. It does a much better job, perhaps a few inches shy of really the true maxima that we saw in that no risk plot. Not quite the 12 to 18 inches, but very close in this 36-hour run. And again, signaling sort of these two maxima south of Buffalo, and again, northwest of Syracuse, there in upstate New York. And also in northern lower Michigan and eastern upper Michigan as well, really bringing on those more aggressive snowfall accumulations better in the HRRX. And as we mentioned before, we really attribute that to sort of two underlying reasons. We're bringing in more realistic lake surface temperatures from the FVCOM, So HRRR version 4 here on the right-hand side, warmer lake surface, and also we have stronger winds over the lake when you compare 10-meter winds with version 4 on the right, version 3 on the left. So stronger winds, bulk aerodynamic arguments argue for larger sensible and latent heat fluxes from the lake surface, and that overall contributes to those much stronger lake effect bands. Just wrapping it up here, if there are any questions, we do have sort of this group email that we welcome feedback, suggestions, or questions to gsd.model.qa@noaa.gov. And also just out earlier this month is a NOAA tech memo that really goes into more details on the RAP and HRRR diagnostic fields available here at this URL. So for anybody who wants to go more into the details of this ever increasing array of diagnostic output we have, you might find that tech memo useful. So that's all I have for today. I'll sit tight for any questions.
Okay, got a question from Shane Kearns. Let me unmute you, Shane. Okay.
Hi, yeah, I just wanted to ask if there was any improvements to the ocean sound temperature schemes as well, or representation.
James, can you start again? I think you accidentally got muted there.
Oh yeah, sorry, I missed the middle part of the question. Something about did I hear ocean soundings? Can you hear me?
Shane, are you there?
Yeah, no, the oceans and the sounds. So like tidal sounds.
Oh, understood. Yeah, so sort of the sounds out east. Understood. If any of the colleagues want to chime in, my sense is that it is better. SSTs are initialized from that NCEP data set. So we've given up using that data set for the Great Lakes initialization, but that still drives the sea surface temperature initialization. And I think that should benefit sort of the saltwater sounds that you're referring to. Other colleagues want to chime in on that?
Kinds of offline programming, because I do think that those are real concerns with people not having access to the internet and being access to the internet. Very real and very real.
Okay, Jeff, hearing none.
Yeah, James, this is Curtis. I guess I'll just chime in. That's correct. We're still using the global, the oceans and the areas in the Bay region. So while we think overall the physics certainly improved, including the fluxes and things like that. Is near
the resources and the staff to do in
Thanks, Curtis.
ways. And if you
All right, any other questions? Having a little trouble with the unmute and some background noise, so put something in the questions or use the raise your hand feature, and I can unmute you. Maybe one. Let me put out there is maybe if you want to, someone wants to comment on the potential downstream impacts to these improvements to the lakes, both the Great Lakes temperatures and the small lakes, on the RTMA, and then downstream from there, the NBM.
So, Curtis, do you want to take that on the RTMA? Curtis,
yeah, sure. Basically, yes, the improved inland lake temperatures is absolutely going to benefit the RTMA for the temperatures in the vicinity of those features. So I think that's going to be a big benefit of the RTMA with this implementation coming up in a few weeks. It'll also, obviously, the HRRR is a contributor to the NBM. So that's also going to be realized, again, as soon as that implementation takes place at the end of May, currently scheduled. So those are definitely going to be downstream systems that will absolutely benefit from the improved lake temperature specification So that's all certainly gonna be realized.
Hey, Jeff, this is Bob in Cleveland. I have a question about that case there for the lake effect snow around Lake Erie. I know initially we showed the observed snow and then we showed the two versions of the model. It's hard for me to recall, did the observation or that analysis from NHRC or wherever it came from, did it have a fair amount of snow near or at the lakeshore? And I noticed the two simulations kind of had a fairly definite, looks like that lakeshore plain didn't have much snow on it. So from the model simulations, I don't know, maybe I'm wrong looking, but here there's quite a bit of snow right up to the lakeshore, and so I don't know. Just a question there. Maybe I know you're talking about that higher wind flow and all. Maybe there's a little bit of extra heat coming into the lakeshore. Maybe I'm getting too particular, probably. It's hard to tell from the view of these maps too.
Yeah, I think you're referring to the relative lag between the lakeshore and the maxima depicted here, and whether that's too far inland or if that should be closer to the lakeshore itself.
Right. Yeah, that's always a hard question. Is that early in the season when the water's warm, sometimes it's hard to get those accumulations on the lakeshore, and I see that you've got a blue ribbon there along the southeast shore of Erie, and also up there in Syracuse's area too, there a bit. So it's just a question. It's always a challenge.
Yeah, I'm not sure, and it's a delicate matter. If we're going to have warmer lake surface temperatures, that is going to have a tendency to keep the temperatures on the lee side shoreline a little bit warmer as well. So that'll have kind of a dampening effect on the snowfall accumulation, all else being equal, even if the snow production is higher.
Yeah, I like that 17-to-1 ratio too that you're ultimately allowing. That's typically what we find here in Northeast Ohio for lake effect snow. So good to see your ratios up to that level for the cold situations, which it's almost always cold with lake effect snow. So
yeah, that's we think it's the way to go. We think it works well in a lot of Western locales too. So we hope it's a good overall general improvement in this variable density accumulation algorithm.
Steve Zubrick, you can unmute yourself.
Yeah, I actually answered my own question. I believe my question was on a comparison of the current HRRR with the operational, or the operational HRRR with the experimental. And I believe on your website that you have, the rapidrefresh.noaa.gov for the HRRR, you do have side-by-side capabilities to compare the two. I think the HRRX is the version 4 that you just discussed.
That's right. Yeah, HRRX is HRRR version 4. It's more or less frozen right now until that implementation occurs.
And there, just a side question. I think there's an NCO version of the HRRR version 4. How different is that from the HRRX?
It should be. We want it to essentially be exact. The reason we're doing that comparison is to make sure that the NCO parallel, which is already running in parallel, is faithfully reproducing HRRX. To the extent that they're a perfect match, it means that we've got the upgrade right and we're ready to go on the 26th.
Okay, thank you.
Yeah, James, I guess I'll just add a little bit to that, we absolutely, what you said is correct, with the caveat that sometimes the GSL HRRX doesn't run smoothly. We're on obviously a R&D supercomputer that has some disruptions periodically, and that can result in some forecast differences. But we're doing our best to try to keep those two as nearly identical as possible.
Yeah, that's a good point, Curtis.
So you all are happy with like the snow melt in the model and keeping the temperatures, some in the past historically there was challenges with keeping the boundary layer too cold when, warm advection was happening, and it wouldn't allow the temperature to rise until the snow was gone in the model. That's all good now?
Yeah, we are
I'm talking
helping.
like an old person here.
Yeah, I didn't show any particular results to that effect, but we are, notably, we are still doing, once a day, we'll do a snow building and trimming. So even if the model has accrued a fairly substantial error in its snow cover, either we're not maintaining snow long enough or we've too quickly melted snow away, every day we have an opportunity to course correct that land surface state and either build snowpack that wasn't there or erode it. And that's a very important aspect to keeping the HRRR from drifting too far away. There's also been some changes to the land surface model and the surface layer scheme that would impact those exchanges between the land, snow-covered land, and the atmosphere. I won't go into that, and I didn't show those results, but we're fairly sure that we've made progress there.
Okay.
Dave Zaff? You should be unmuted. Oh, Dave's got no mic. Okay, so Cleveland is right. Cap 17-1 is better, but for lake effect, we can get much higher. Dave is in Buffalo. Any thoughts on convective snow, lake effect snow, which often gives higher ratios in lake effect events?
Yeah, we think that, yeah, perhaps that ratio isn't quite right. The 17, perhaps it should be higher. But notwithstanding that, we think that for the reasons I mentioned, lake surface temperatures, over lake winds, and with a lot of scrutiny by our colleagues in Glaral, the WFO at Detroit, of course not an eastern region, that we're getting the basic band structure, band intensity, and placement right. So even if the variable density snow ratios aren't perhaps what they should be in the most extreme events, we think we're going into that algorithm with better information to start with from the model physics.
Hey, James, this is Ed. If I get.
Yeah, we hear you, Ed.
Yeah, I'll make a quick comment here. And Trevor is one of the keys, and John Brown working with this, and we could certainly make this a lot more sophisticated. It's still a relatively simple algorithm, and I'll mention, and that would if you had a lot of dendrites, et cetera, it could then give you a much even higher ratio. We get higher ratios out here all the time. One other aspect, though, of this that we did change that's kind of important, I think, is notice how the SLR is a little higher as we get towards zero. When I looked at a lot of cases, I thought we were killing a lot of the snow, even below freezing. So this will help in that regard. But yes, we could make this better. One question I guess I had for Curtis and the group is, as we make other changes, will they show up in HRRX experimentally down the road, or what's the future of that?
I can try to handle that one, Ed. Obviously, this is the final ARW-based HRRR implementation with version 4 happening at NCEP. So we are pivoting, as I think was mentioned here with James, to an FV3-based 3-kilometer system as part of what's known or going to be known as RRFS, Rapid Refresh Forecast System, that's planned to subsume the NAM, the RAP, the NAM nests, the HRRR, high-res windows, all into one regional forecast system with an implementation in 2023. So in the short term, after this HRRRv4 implementation happens at NCEP, the HRRX becomes a tool for us to start evaluating ultimately FV3 capabilities and physics changes that we're going to continue to be developing along with data assimilation changes. So we have to figure out exactly what role the HRRX plays. I think we're going to continue, having it as a real-time parallel, but we might start recasting it as RRFSX. So it becomes an experimental prototype for that system that forecasters can look at and become an FV3-based system. But we're still a little ways from making those types of changes. But I think that's what's going to happen here in the coming months and year.
All right, any other questions?
I guess I have a question about convective initiation. You all mentioned that there may be more realistic evolution of perhaps QLCSs. Is there improvements in convective initiation, timing, location, maybe even cloud top heights? It's just sort of an aviation question, I guess.
Yeah, we think most notably for what we would sort of say the strongly forced or organized convection, like I showed, QLCS. We're still not entirely happy with sort of convection in a weakly forced environment. Think of like the southeast and midsummer, low shear, high cape, those daily thunderstorms. So in those environments, we don't quite see the convective coverage we want. We don't think we've taken a step backward, but we certainly think that it's in these organized, more strongly forced scenarios like I showed, that the convective initiation is better, convective maintenance, and for the reasons I illustrated, such as relaxing of the microphysics temperature tendency, that the actual storm morphology is better as well. So cloud tops, the storm intensity. We have a hailcast diagnostic algorithm, which is essentially a 1D hail embryo growth model that's now available in the GRIB2 output, largely from work done by Becky Adams-Sellen at AER. So we have this hail diagnostic inline now, and that's really benefiting from these stronger updrafts that we have now that we're able to really throttle up the heating tendency. So all in all, we think the storm structures are better, but again, most notably for the well-organized, strongly forced convection.
Okay, the last question I have, it has to do with the soil moisture. I think that initialization scheme that you have running, it sounds like it's sort of a missing link where I guess you're tracking rainfall, observe rainfall, red or dry, to try to track some sort of soil moisture, or then you have some other estimations of it or guesses, I guess, to deal with error in that. Is that what's happening there?
Yeah, so the land surface state in both the RAP and the HRRR are continuously cycled from hour to hour. So for example, when it rains, we will wet the soil. But if those errors develop, the data assimilation scheme can do soil moistening or soil drying, as well as adjust the soil temperature. That's most strongly driven by METAR observations. So we don't actually assimilate observations of soil moisture or soil temperature. What we really attempt to do is use surface observations and then do some attribution. So if, for example, our METAR station says that we are too warm and too dry, not only will we adjust the atmospheric state, but we will adjust the underlying soil state. And so that's how we can cycle land surface states in perpetuity without drifting too far from reality.
Okay, so and you're using the METAR, since they're updating all the time. The HRRRAS would only be like once a day or whatever, I guess, unless you use more at 12 or something.
Yeah, that's right. It's really sort of METAR-like obs, Mesonet. It's going to be those observations that are most indirectly helping constrain our land surface state when errors are encountered.
Okay, thank you.
Ken Johnson?
Yeah, thanks, Jeff. Thanks, James. This is a great little presentation that you gave. Appreciate you doing it. Early in your presentation, you gave you showed some slides with all the observations you assimilate into the model initialization. And I noted aircraft observations in there, which is kind of an obvious thing. And I guess just a question related to the times we're in right now. Have you noticed any impact upon mesoscale simulations here due to the loss of aircraft observations as a result of fewer flights? And if so, could you attribute it to perhaps loss of observations with either ascent or descent, in other words, more in the lower levels of the atmosphere, or would there be other reasons why it would have an impact?
Yeah, that's a great question. maybe Eric James, who's done some aircraft DA work, or any of the other DA colleagues on the line want to tackle that?
Yeah, this is Eric James. Can you guys hear me?
Yes.
Yes, yes.
Yeah, so we have been carefully watching our statistics over the past month to see if we can detect any signal of the decrease in volume of aircraft observations. It's been pretty hard to detect. Of course, we don't have a controlled experiment, but weather is changing every day. So we can just look at time series and see if we see any statistically significant changes in our forecast skill. We haven't actually seen that yet. I have recently done a data denial experiment where I switched off approximately the same fraction of aircraft observations that is now grounded, that just to try to represent what's happening in reality. And I did see an impact there. So I'm working on getting that published. But to answer your question, no, we haven't seen any real-time impacts yet, but we think we may be limited our verification metrics that we have available to us. And so we have some ideas for trying to expand our verification capabilities to look at the frequency of like high error events, cases where there's larger errors than, you know, a certain threshold. So we may be able to see something there, but we haven't found anything at this point. But that's a good point.
Okay. Yeah, just curious, in your data denial experiment, what's the nature of the differences that you're seeing?
So our verification was against radiosondes, and we saw definitely statistically significant degradations over the whole CONUS domain, as for wind forecasts, temperature forecasts, and relative humidity forecasts. When like 75% of the aircraft observations were switched off. So we think that there are likely some impacts happening. They're just difficult to detect with these time series and without a controlled experiment.
Oh, interesting. Well, thank you.
Yeah.
Any other questions?
Hey, Jeff, this is Ed again.
Ed.
I just want to make one comment. James showed the feedback with the email. We are also attempting to improve our VLab presence. So any comments about that or suggestions are welcome in that regard.
Certainly not a VLab is back.
Yeah, we're trying to make it a little bit, trying to update it. I've been trying to do that, and I know that VLab was down for a while, but I'm not totally sure how much it gets used. And if anybody has comments on that, you know, now or later, or to send me or the group, that'd be great.
All right, thanks, Ed. Anyone else? All right, well, thank you very much, James and everyone at GSL. Really appreciate it. Our next session, I guess, will be on Monday afternoon.
Yeah, I think Tara Lagwade had